Hi, I'd like to go over a problem with you today called weighted activity select. Now, there is a version of this problem where you have activities in this manner and they don't have weights. In other words, there aren't any numbers ascribed to any of the intervals. In that case, you want to maximize how many intervals you can include. However, that ends up breaking down as far as the solution for solving that problem is concerned when there are weights attached to the intervals. And so the weighted activity selection problem, by of course using dynamic programming, is an algorithm to maximize how much overall utility you can derive by choosing a combination of activities. You can imagine that if we chose, let's say, this activity, and this activity, that would give you a certain cumulative sum across the choices you made for those activities. Naturally, if you chose this one, and this one, that would give you, of course, a cumulative sum as well. You'd add the weights that belong to those activities. And so this problem then is about choosing the optimal set so as to maximize the overall cumulative sum across the activities you have. How do you do that? Well, the formalism is that you have something called an opt array. And the opt array is, in a sense, an answer to subproblems for such a problem. So the indices here on this opt array are intervals. And the value at these intervals describes what the optimal numeric number is up to that interval. So for instance, if I'm looking at index 4, then the number here will be the max value of utility I can arrive at up until that interval 4. So if I'm at 4 here, I'm looking at what number belongs there. It will be the max value of utility that I can combo up until that interval 4. And so that's the way it works. So opt of 6, the number that belongs here, will be the max value that you can gather up until activity 6. Now that of course might be by using certain intervals or discarding certain intervals, but nevertheless, up until, let's say, interval 6, you will have an answer here for the overall max value that you can get up until interval 6, or even very well including interval 6, for what the max value is. Now, when I say max value, I'm referring to the maximum overall utility across intervals up until or including interval 6. So that's the opt array. And in a sense, that's what we want, right? We want to be able to point out and say, okay, well, up until interval 7, what in fact is the overall max utility you can get up until interval 7? Now, I say that's useful because ultimately we're solving for the entire problem, which is to know, given 8 activities or given overall 7 activities, what's the max value? That final answer will rest in that last position. We also have a choices array. Just because I said that you can be able to point out an interval and then say what the max overall cumulative sum is up until that interval, that doesn't necessarily mean you know what intervals went into producing that maximal optimal value. And so the choices array will actually tell us whether or not an interval was chosen as part of an optimal solution up until a particular interval. This is, of course, a Boolean array that will hold true or false. And it will be true if the interval was chosen. It will be false otherwise. There's also a P array. And P array, so let's say if I had P of I is the closest non-conflicting interval for a particular interval I. So for instance, if I have V of 5 here, which is equal to 2, the closest non-conflicting interval is V of 3, right? So that is what that gives us. And I'll describe why it's useful to have that at hand. But nevertheless, if I have V of 5 equal to 2, this is the 5th interval here in my interval set. If I wanted to know the closest non-conflicting interval behind it, I would have access to that. And that ends up actually being important for solving this problem, and I'll tell you precisely why. But nevertheless, you should know that P of I will give you the closest non-conflicting interval for a given interval of your choice. Nevertheless, how do you solve this problem? In other words, how do you start populating the octarray? How do you, in fact, gain this ability to say, okay, well, up until interval 7, 8 or 10 or 12 is the max optimal value in a numeric sense that was gathered up until interval 7 across all intervals that could be used. How do you do that? The formalism is actually relatively simple here. For any given opt of I, you're going to take, there are two possible options. Either opt of I can be the optimal solution for the interval that you're looking at, -1. That's just a fancy way for saying, look at the previous interval, and that, in fact, whatever optimal solution rests there will, in fact, be the optimal solution up until that interval. In that case, we're not including the interval that we're concerned about. Or it will be the optimal solution of the value of the interval plus the optimal solution up until the most recent non-conflicting interval. So I want to unpack that just to be clear. Either the optimal solution is the interval that just came before it, right? Either the optimal solution is the optimal solution for the interval that just came before it. So if, let's say if I was on V of 5, either it will be the optimal solution for the interval that was directly before, in this case, that's V of 4, right? So if I wanted to figure out what the optimal solution is up until V of 5, it might as well just be V of 4. Or it could be the value of that interval, which in this case is 2, plus the optimal solution up until the closest non-conflicting interval, which in this case is V of 3. So you end up taking the max of both of these, right? Whichever is bigger will end up being your answer. Either it's the optimal solution for the interval directly before it, or it's the optimal solution of the closest non-conflicting interval, whatever the optimal solution was there, plus the value of the interval that you're asking this question for. And so you end up taking the max of whichever is big. You end up taking the max of both, but conclusively you take the max and then you end up choosing whichever is bigger because you're applying a max function on both of those numbers. Let's actually see that in action. So let's say I have V of 1 equals 2. And by the way, the base case here is that the first element, V of 0, opt of 0 is 0. The optimal solution for choosing no activities is no activities in a numeric sense. But nevertheless, we're on V of 1 equals 2, and we ask ourselves, well, gee, opt of, in this case, it's 1, right? Opt of 1 can be two things. Either it's the optimal solution for the interval before there's nothing, or it's the optimal solution, or it's the value of that interval plus the optimal solution of everything that came before it in terms of the closest non-conflicting interval. Now, there are no intervals beforehand, so it's just 2, right? That's kind of pretty apparent. For V of 2, right, either it's the optimal solution directly before it, or it's the value of the interval plus the optimal solution for the closest non-conflicting interval. There are no non-conflicting intervals here, so it'll just end up being the value of the interval itself. Now, actually, V3 equals 4, this is where things start to get interesting. So either the optimal solution of the closest non-conflicting interval, right, plus that interval number. So we know that's 2, right? Plus 4. So that's a contender, right? That's a contender. we're looking at that interval and we're saying, well, either it's the value of the interval, which is 4, plus the value of that interval's p of I, right, which is 1, right? So that ends up actually being the solution here, right? It's 6. Either it's the optimal solution of the interval directly before it, which is 4, or it's the optimal solution for this interval's p of I, which is 2, plus the interval value itself, right? So far, we have 2, 4, 6. We can now look at interval 4 here, right? Either there are two options, right? Either it's the optimal solution for the interval directly before it, which in this case is v of 3. We know that the optimal solution for v of 3 was 6, right? Or it's the interval itself, interval value itself, 7, plus this interval's p of I, the closest non-conflicting interval, right? The closest non-conflicting interval, in fact, there are none, right? So quite simply, we would just put 7, right? Now, for interval 5 here, right, either it's the optimal solution of the interval that came before it, which is 7, so it's either going to be 7, or it will be 2, which is the value of that interval, plus the optimal solution of the closest non-conflicting interval, which is v3. Now at v3, there it was 6. 6 plus 7 is 6 plus 2 is a pretty good answer here, right? So we took the optimal solution of the closest non-conflicting interval plus the value of the interval itself. That was bigger than the optimal solution for the value that came, for the interval that came before it. And so we populated it in that manner. Now for interval 6, again, you kind of have that same binary choice. It's either the optimal solution for the interval that came before it. We know that's 8, right? Or it's the optimal solution of the closest non-conflicting interval, right? Which is v3 equals 4. We know that was 7, right? Plus the interval itself, which is 1. So, between both of those numbers, they're actually equal. And that would be the optimal solution then, right? So we were on v6, we said, okay, well, it's either the optimal solution of what v5 was, which is 8, or it's the optimal solution up until v3, which is 6 plus 1, which is 7. So actually it's 7, right? And so we just put 8 there, 6 wasn't included. Now, the choices array and the p array, these ideally should have been filled before we got into the problem, but nevertheless, it's something we can do. P of 0 is 0. And again, you're just noting down the interval number for the closest non-conflicting interval. P of 1, like what's the closest non-conflicting interval? P of 1, it's nothing. Here, v2, what's the closest non-conflicting interval? Well, it's nothing, right? And then for 3, the closest non-conflicting interval is interval 1. So we put 1. For 4, the closest non-conflicting interval is, quite honestly, nothing. For 5, the closest non-conflicting interval is interval 3. For 6, the closest non-conflicting interval is, in fact, interval 3. Right? And so 0, 0, 0, 1,
0.033.
Now, of course, as you were doing this, as you were populating the opt-array, you should have kept track of whether or not the interval was in fact in the optimal solution. Like when we were doing v of 1 equals 2, we said, okay, well, let's include that, right? When we were doing v of 2 equals 4, we said, okay, in and of itself, it's sufficient. We included it. When we were doing v of 3, we said, okay, well, we have two choices. It'll either be, the optimal solution of the interval directly before it, which is 4, or it'll be the value of the interval itself, which is 4, plus the value of the closest non-conflicting interval, which is v of 1. So 2 plus 4, that's 6. That beats v of 2, which is 4. So, we chose it as well. So v of 3 was, so all these intervals, sorry, the first interval, v of 0 is not, c of 0 is not chosen. So these are true. V4 is also true in its own sense. V5, we chose it as part of the optimal solution. V6, that's where we said, actually, you know what? At V6, there are two options. You can either choose to do the optimal solution of the interval directly before it, V5, which in this case is 8, right? Or you can count value of that interval, which is 1, plus the value of the optimal solution of the least of the closest non-conflicting interval, which is V3 is 6, that was 7. So 8 went out. We didn't include V6, and so ultimately we marked that as false. This actually happens to be everything you need to backtrack, because let's say you can start at, let's say I want to backtrack for, at interval 6, what intervals went into the optimal solution for interval 6. In that case, you can start here. You can say, okay, well, choices if I is false. Fair enough, then I won't choose interval 6 in my optimal solution array. Seems like I choose interval 5 though, because it says true there. So I would print out interval 5. Now, when you're at interval 5, it's like, well, which new interval do you check? I mean, which interval do you now check to judge whether or not it should be included? Should it really be intervals that conflict with it in the meantime? Not really, right? So you want to know which interval now should you go to check. That will be given to you by P of I. So, now that you've chosen an interval, you need to say, okay, well, what's the fifth interval? What's interval number 5's P of I, right? Where do I jump to? I want to jump to where it's closest, but it doesn't conflict, which is given to me by P of I. So if I do P of 5, I'll know which interval to jump to. P of 5 is 3. So, 3 is in the solution as well. So I'll take interval 3 as well as part of the optimal solution. Well, okay, fair enough. I did that. I know P of 3. I know 3 as an interval number is in the optimal solution, but where do I jump to now? I'll have to jump to a place where, the first interval that does not conflict with 3, that happens to be P of 3, right? So P of 3 is 1. And so that's the first interval. Was the first interval in the optimal solution? Yes, it was. So, use interval 1. Okay, well, where do I jump to now? It would have to be the first interval is P of I, so P of 1 is 0. We terminate 0 is false. It's not in the optimal set. And therefore, the solution to backtrack from interval 6 is in fact interval 5, interval 3, and interval 1 as being constituents in the optimal solution. Runtime. Generally speaking, the runtime is order of n times the time it takes to actually execute on P of I. P of I, you can imagine for each interval you go through, you're running a P of I check. So in the worst case, that could be n elements, and therefore it's actually order of n squared. But then if you use binary search to optimize the P of I function, you actually bring the P of I function to an O log n time. And then for n elements, it ends up being O of n log n as an overall time complexity for this algorithm.